We're going to look at the general first order systems in this video, so it's quite handy to take a look from a higher level down onto what we're doing. It helps us to see the wood for the trees and gives us a general understanding of what's going on, and I think helps in the end to aid all of our understanding. So a first order system means that there's only one energy storing element. So in this case, the energy storing element is going to be, in the electrical system, is going to be an inductance or a capacitance. So we've seen there that the voltage is equal to L di by dt for an inductor, and the current is equal to C dV by dt for a capacitor. Now we're not really dealing with inductors, we're not getting any inductors in this course. So it's really only the capacitance we're dealing with here. But what we want to do is we want to look at the most general type of first order system. So the best way to do that is to look at a differential equation that defines that first order system. So here's a simple first order system, a differential equation. So you're going to have an input function y of t and an output function y of t and an input function x of t, and these a0, a1, b0, b1s, these are constants. In our case here, the constants are going to be determined by the resistance and the capacitance of our circuits, and you'll see that the input and output has been split into x of t and x derived of t. It's just to keep it as general as possible, because we're looking at the first order, which is going to have a rate of change here, so the first rate of change. So we look at the input as being made up as a function and the first rate of change of the function, and the same as the output. It just keeps it as general as possible, but you'll see where it fits in when we work through the rest of this. So now what we want to be able to do is we're going to use our ideas of Laplace transforms to try and simplify things, because we don't want to be dealing with differential equations. We want to deal just in case in terms of algebraic equations. So we can do that by replacing our y of t by the complex frequency equivalent of y of s, and the y derived of t by s y of s. So we know that differentiation, if we go to the complex frequency domains, it equivalent to multiplication by s, and that, as we said before, that's the whole point of doing this. It makes all the mathematics a lot easier, because now we're only dealing with simple algebraic equations here as opposed to a differential equation up there, and the same goes at the other side. So what we're interested in is a transfer function. So we're interested in how the output changes dependent on the input, so we call it a transfer function h of s. So we could take our common factor and y of s out of here, and you're just going to be left with your a0 plus a1s, and you could take the common factor of x of s out of this, and you're left with the b0 and b1s, and then you can divide the y of s by the x of s, and you'll just be left with the b1s plus b0 upon a1s plus a0. So it's good doing this, because we're getting a completely general transfer function that defines all first order system transfer functions. Now what we're interested in is looking at the poles and zeros in the complex plane. So we know that we're going to get a pole, that is, we're going to get a maximum value for this h of s whenever the denominator is equal to 0. When that's equal to 0, this tends off to infinity. So in order to make that equal to 0, we can say that s is going to equal minus a0 upon a1. Okay, that's going to make this whole bottom line equal 0. So that means that h of s will tend to infinity, so we're going to have a pole. And similarly, we're going to have a 0 whenever the top line is equal to 0. So when s equals minus b0 and b1, then h of s is going to tend to 0, so we're going to have a 0. So the idea here is that a first order system, it's got at most one pole and one zero, and the position of the poles and zeros are what determines the response of the system to an input. So let's continue with this, and we'll look at the positioning of our poles and zeros. So I have another course there called Fourier and Laplace Transforms. There's over 45 videos, and it goes into all the details about the position of poles and zeros and exactly what it means. But it's just a little summary here. If you're interested, you can go and have a look at that other course. But there's the summary really here says that for a real function of time, because we're only really dealing with real functions of time, we don't deal with complex functions of time. So for a real function of time, the pole and the zero must lie on the sigma axis. And for stability, the pole must lie on the minus sigma axis. So it means that we can fix the pole on the minus sigma axis, and we'll adjust the zero along the sigma axis, so the plus and minus sigma, and we'll have a look and see what the frequency and phase response are going to be like. Okay, so we'll start off here, and we'll note that the response here, the frequency response, we can find that from the complex frequency transfer function by simply making the sigma equal to 0. So and that really boils down to replacing the value of s with the value of j omega. So this here is going to give us our frequency response. Now the way we want to think about this here is that this axis here is j omega, and that's the sigma, and that there's the magnitude of the transfer function. So this is the S plane here, and we can kind of think about it as an elastic surface which can be moved. Okay, so you can place your finger in it, push it up, and it's going to affect the rest of the surface round about it because of this elasticity. Now what we're going to do here is, as we've seen here, we're going to look at the pole and zero position on that complex plane, and we're going to look at the magnitude response, we're going to look at the phase response. So we fixed the pole here on the minus sigma axis, so the big cross here is the pole, and it's fixed all the way down this minus sigma axis. And we're going to adjust the position of the zero. So the zero's in blue, so the zero might start off at minus infinity and come down towards and eventually sit on top of the pole, and then it will come down further onto the crossover point between the j omega and the sigma axis, and then it will head off down towards minus infinity. So let's have a wee look and see what happens as we do that. So if the pole is, the zero is sitting off at minus infinity, then the pole here is going to dominate, and we're going to get a low pass section like this, and we're going to get a phase response, and that's our phase response drawn there. Now if we move the zero down onto the pole, when the zero sits on the pole, they cancel each other out, and we just get an all pass section with no frequency response. Now if we were to shift the zero down past the pole and onto the j omega axis, then we're going to have a zero on the j omega axis, so we're going to have, it's going to look like a high pass section. Okay, the frequencies are going to be cut out at the low frequencies, and they'll pass at the high frequencies, and also there's going to be a phase response associated with it. Now if we were to move the zero so it's equidistant from the pole, again they would cancel each other out, and we would get an all pass section, but the all pass section is slightly different because there would be a phase response associated with it. And then if we were to move the zero off to plus infinity, then the pole is going to dominate, and we're going to have a low pass function, and the phase response is going to be different from the original low pass function we've seen up at the top. Okay, so that there is just a kind of nice kind of hand waving description of what happens to the pole zero positions in a first order system and how it affects the frequency response. Now, just another note that I've seen this a few times, but it's always worthwhile to repeat it. When we look at the frequency and phase response, what we're looking at is a frequency axis omega, and we're looking at an imaginary part of that signal and the real part of the signal. So the actual signal is going to be rotating round about this axis. So obviously the further it goes up this axis, the quicker these phasors rotate. But if we were looking at this from this side in, okay, so we're looking at it from this side in, then we can find the magnitude of this response, and the magnitude of the response is going to be equal to, simply by Pythagoras, which is the imaginary part here squared plus the real part squared, and if we take the square root we get the length of that blue line. So if you like, we're looking in this direction, and we're looking at the shadow that this casts in that direction, and this is the shadow that it casts, and that there is going to be the magnitude response. And of course there's going to be a phase response associated with as well. So this graph here, this shows you how the phase changes with the frequency. In effect, it shows you how what the angle's like as this rotates round, okay, as you move up in frequency. So that's all there is to this video. It's just a nice overview, and whenever we go on and we look at the next video, which will be on a low pass filter, we'll just work through the low pass filter, and then we'll see how all of the low pass filter terms relate to this general first order system. Okay, thank you for listening, and goodbye.